Okay, up to here you have learned how to use the thermodynamic properties uh, tables to find the different properties for different substances in different states, which the states or region which up to now I have introduced you are the saturated liquid line, saturated vapor line, and also the mixture of the saturated liquid and vapor. Today, in this slide, I'm going to tell you more about superheated vapor, about this region. You already know about this region. In previous session, we have discussed about this region, the region which the temperature uh, or the according to temperature and the pressure of the substance, it has some specific characteristics. But first of all, how we can now know if the substance is in the superheated vapor region or not? To find and understand this question, to answer to this question, if the substance is in the superheated region or not, we need to check these different conditions. So we need to uh, characterize actually the superheated uh, substance, superheated vapor for a substance by checking these conditions. First of all, we should check if the pressure of the substance is lower than the saturation pressure at a given temperature. And how where we can find this saturation pressure or uh, in each temperature, we need to refer to those things. So anytime we are going to understand if about the region or a state of a substance, we need to check this table A4 or even table A5, according to the information which we can get from the question here. The first one, we need to refer to the table A4. Let me just go to table A4. You can see here we have temperature. So the temperature is given, and also we have saturation pressure. If the pressure which we have for that substance is less than this saturation pressure for each one of these for the given temperature, it means it is in the superheated region. And also we can check with the temperature. If in high temperatures also we have superheated vapor. But what is this high? What we mean of this high? Again, we can check with table, this time with table A5. In table A5, if we go to table A5, we have different pressure and we have saturation temperature for the respective pressure. So we have pressure, then also the temperature is given. First, we should find the pressure in this table, and then we should find the saturation temperature for that pressure. Then we can compare the temperature which is given in the question with the pressure, with the temperature, saturation temperature at that pressure. So this is just two methods we can check if the substance is in the superheated region or not. And also in higher specific volume. Again, from those table A4 or table A5, we can go there and find the VG. If the specific volume, which for the substance which we have is higher than the uh, uh, VG or a specific volume of saturated vapor for that saturated vapor for that substance in the given temperature, we can again understand that it is in the superheated region. Same about the higher internal energy. If internal energy is higher than uh, specific internal energy uh, for saturated vapor at uh, that pressure or temperature. In other words, all of these Vg, Ug, Hg are on this line. So we are going to beyond this line means it is in the superheated region. So if here we have Hg and also we have Ug, we have also Vg in this point, for example. So if, for example, in this, for example, for this pressure, if the H U or V which we have is higher than HU or V, each one of them, higher than uh, that for the saturated vapor, it means it is in the saturated vapor. So simply and easily we can understand if it is in the state of the substance is if it is in the superheated region or not by using these two tables. This is first step, and by this method we can understand if it is in the superheated region or not. Then if we understand, okay, it is in the superheated region, how we can find uh, the properties which we need for this superheated region. For example, this point which is the in the superheated region. So how much is V for that? How much is U for that? How much is the enthalpy for that state? Again, we have another table which is table A6. In table A6, we have for different temperature, actually different saturation temperature, and for different pressure, we we have this property VUH, or the specific volume, specific internal energy, and specific enthalpy for superheated region can be found in this table. This table, this is just part of that table. Let me just show you the whole table. Here we have superheated water. This table is for water. However, we have this table also for other substances as well. So you can see here the saturation temperature. So we have temperature, for example, and also we have pressure. Then simply we can come to this table and find VUH, and later we will have also SL or entropy. So this is the table for superheated uh, state. If first we should check if the state of material is superheated or not by those conditions which I told you. These conditions, we need to check these conditions. Then if it is approved that the state is in the superheated region, we need to go to these tables to find the find these properties for that state. So here I have, by this I introduce you this table A6, which is for the superheated vapor. Next, I'm going to show you an example to how to use this table. But before that, I should tell you something more about these tables. If you notice, in these different tables, table A4, for example, we have temperatures here and also pressure. But if you notice here, the temperature starts with, for example, this 0.01 degrees Celsius, then 5 degrees Celsius, 10 degrees Celsius, 15 degrees Celsius, and so on. It is increasing by 5 degrees Celsius steps. And you can see here, for example, how about temperature when temperature is 8 degrees Celsius? How about what are these properties for temperature uh, 27, for example? We don't have that or those values in these tables. What we can do is to do an interpolation. Interpolation is a method which is also for other table. Let me just also show the other table for to you. We have you can see here 4 kilopascal, 5 kilopascal, and so on. 10, then 15, 15, 20. What about 18 kilopascal? How we can find these properties for that pressure? And even in table A6, you can see here we have 200, 250, 300 degrees Celsius as saturation temperature. But what about the 220 degrees Celsius, for example? How about the other temperature? So let's see how we can find the values or properties for the temperature or pressure which are not in the table. We use a method which is interpolation method to find properties or different properties for a temperature or pressure which is not presented directly in the table. For sure, if you notice here, for example, we have 100 degrees Celsius, then this 100 degrees Celsius, this is 150 degrees Celsius. So the amount, if the temperature which we have is, for example, 120 degrees Celsius, temperature is here for sure. The V or specific volume will be between these two values, and also U will be between this one also between these two values. Why? Because it is assumed that the if you remember about the different figure which we had, different temperature. This is mm, how this is for pressure, for example. Imagine we have different pressure. If you remember, the line for different pressure was the trend was similar. The only difference was in uh, the length of this phase change process or change in the specific volume or here specific enthalpy. So that we, if we just draw a line like this, you can see here like this. For example, we have, imagine we have, imagine we have this for these 2 points. We have the pressure and also we have the property. Or we have the properties for these two pressure. This is P1 line. This is a P2. Okay, let me just change here. Okay, imagine this is P1. This is P2. Then this will be H2. This will be H1. If we draw a line like this, you can see here it will be like this. So H1, H2. Then what about P3, which is between these two? It will be like this. So H3, this point for sure will be between H1 and H2 for a pressure which is uh, P3, which is between P1 and P2. So simply by this interpolation method, we can find the properties for the state which we don't have in this table, for the temperature, different temperature, which is not in the table, and also for the pressure, which may not be in the table, for example, in table A5. Let's see how we can do this interpolation process. I use a video which is prepared and it will help you to understand how you can do this interpolation. However, this method is being used in other branches of science, and the method is very useful to find the thermodynamics properties in the thermodynamics table properties table as well. So let's see in this video how we can use this interpolation method.
So this tutorial is all about how to interpolate, and in particular how to interpolate between values in steam tables. So we start out by considering two values in the steam table that each have a value which we'll represent by x1 and y1. So this could be temperature and pressure, or enthalpy and pressure, any two variables. If we assume that that variable varies linearly between the two tabulated points, then we can calculate the slope of that line. So obviously the slope is given by y2 minus y1 over x2 minus x1. If we're then given some value x that is between our two tabulated values of x1 and x2, we want to know what is the corresponding value of y. So very simply we can calculate that value of y using y1, the slope of our line, and the difference between x and x1. So if we expand that using the expression for slope from above, we get this expression, which is the expression that we'll use for interpolating in the steam tables to find values between two values. So if we look at our first example, we're going to calculate what is HF, what is the fluid enthalpy at 0.05 bar for saturated water. So we can see that 0.057 bar fits between these two values, and so the enthalpy will be between 145 and 152. So just writing those two values down, because we're not going to be referring back to the table, the enthalpy of saturated water at 0.055 bar was 145 joules per kilogram, and at 0.060 bar was 152 joules per kilogram. So if we just substitute those values into our expression that we derived earlier, we can directly calculate the enthalpy of saturated water at 0.057 bar. So it's 145 plus the slope of the line multiplied by that difference in x, which is 0.057 minus 0.055. When we calculate that, we get 147.8 joules per kilogram. That should be joules. When we check that, we can see that the value we've calculated sits between the two tabulated values, and that's as it should be. Okay, if you get a value that sits outside either of those two values, then obviously you've made some kind of mistake. So that makes sense, and that's good. We'll do a second example, working back in the other direction. So if we are given the enthalpy and we want to work out, for example, what is the saturation pressure, we can also do that. So here we'll try and find the saturation pressure for liquid water where the enthalpy is 132 joules per kilogram. So we can see that 132 joules per kilogram sits between 130 and 138, so our saturation pressure will be between those two values. So the saturation pressure of water with an enthalpy of 130 joules per kilogram is 0.045 bar, and the saturation pressure of saturated water with 138 joules per kilogram enthalpy is 0.050 bar. So substituting those two values into our equation that we derived earlier, we can directly calculate what is the saturation pressure of water that has a enthalpy of 132 joules per kilogram. And it's just 0.045 plus the slope of the line multiplied by the difference x minus x1. So if we calculate that, we get 0.04625 bar, and checking, we can see that that sits in here between the values 0.045 and 0.05, so that makes sense. and that's good.
In this example, we are going to see how we can use table for the superheated vapor. The question is we need to determine the temperature of water at a state of uh, with this pressure P is equal to zero point 0.5 megapascal, and also the enthalpy of that uh, state for water is 2890 kilojoule per kilogram. So what we should do, according to what I told you in previous slides, we need to check first of all if what is the region or a state for uh, water at this pressure, and also these with this enthalpy. What we should do is, because here we have pressure and also enthalpy, so first thing we need to do is to go to the table which we have for saturated water according to the pressure, because we have pressure which is table A5. Then we should compare H, which we have here. You know, here you can see here it is not mentioned which it is HF, HG, or in the mixture. Yeah, it is only H. So we need to compare this H with this enthalpy with the enthalpy for water at this pressure. So let's go to the table which we have for saturated water and this pressure. Okay, pressure is uh, zero point 0.5 megapascal or 500 kilopascal. Okay, here if we check the pressure, this is saturated water pressure table, and here the first column is the pressure. So let's find the pressure which for our question is 500 kilopascal, zero point 0.5 megapascal or 500 kilopascal. You can see here we have the pressure here, and we need to find H or enthalpy for this. So you can see here Hg and Hf we have here. So let's compare these values. So we can record these values. Then let's go back to the question. The H which we have is 2890 kilojoule per kilogram, and the Hg which we have recorded already, we saw this. We have seen this Hg in the table A5. It was equal to 2748.1 kilojoule per kilogram. By comparing H and Hg, you can see here H, which enthalpy which we have for this state, is higher than uh, enthalpy for saturated vapor, and it means this the water in this state is superheated vapor. So the state is determined. Uh, to find the temperature of water in superheated region, we need to refer to the table related to the superheated water. The table which was for superheated water was table A6. If you remember, we have this table for superheated water, and for different temperature and different pressure. Okay, the pressure which we have here is uh, 500 kilopascal or zero point 0.5 megapascal. Let's see if we have that in this table. Uh, Actually, this table start. This is the part of table A6. This table start in previous slide. So let's just find zero point 0.5 megapascal. Okay, it is here 0.5 megapascal. We found the pressure which we have. Now what we should do, what we are going to find in this table is the temperature of the water with dispersion, and also we have the enthalpy. Enthalpy also is given in the question. Okay, now let's go back to the question. Here you can see the H which we have here. This is our H. This is actually this is our H. H is equal to 2890. Let's just go to the table which we have here. Table A6, H was 2890 kilojoule per kilogram. Just double check if I am right. 2890 kilojoule per kilogram. Okay, this is our H. And the pressure which we have is 0.5 megapascal. Now let's see for which one of these temperatures the H is this much. This is H, the third column, this is H. So you can see here we have 2748.1, which is less than our H we have here. And after that, the H is 2855, which is still less than our enthalpy. The next is 2961, which is higher than our enthalpy. So the enthalpy for water, which we have here with this pressure and this enthalpy, should be between these two, and its temperature should be also between these two temperatures. So what we need to do is to find the temperature, because here we have the enthalpy. Our enthalpy is between these two, and also we have the temperatures for those two enthalpies. Then we need to find the temperature which is for this enthalpy according to our enthalpy. What we need to do is to use interpolation or linear interpolation. According to video which you have already seen, we can do a linear interpolation to find the value for the temperature of the enthalpy which we have here. Let's see how we can do this interpolation. We found the temperatures and also enthalpies which we require to do interpolation to find the respective temperature for the enthalpy which we have here. So you can see here these enthalpies between these two enthalpies, and also the temperature should be here. Here we have 1890 kilojoule per kilogram. Okay, let's do the interpolation with the method which we have learned in the previous slides. So let's do these interpolations. First, we can write like this. First, you need to actually to draw a table like this. I mean, you need to write like this. You need to find all of them, then write like this table. Then you need to write according to the noun and unknown which you have. For example, here the T is unknown, so simply I write like this. Temperature for this enthalpy is equal to 200 degrees Celsius. For this temperature for this enthalpy we don't have. This is the question actually. And temperature for this enthalpy we have 2961 kilojoule per kilogram is 250 degrees Celsius. Okay, so we have this. Then let's write the equation for interpolation. Simply we can write this equation. temperature of 2890 kilojoule per kilogram of enthalpy is equal to write like this 200 plus the slope, which is the this minus this, and also the temperature. So let's just write this minus 200 divided by 2961 minus 2890. This should be multiplied by this 2890 minus the value for the lower temperature 1800 55.8. Okay, so you can see here we have the equation. If we solve this equation, the result for this will be 216.3 degrees Celsius. Let me just double check the values. Yeah, it's okay. So this is the temperature which we were looking for the state which we have. The information which we have in this, which we had for this example, was the uh, enthalpy and pressure for water. First, we checked and understood that the state of the water with this pressure and this enthalpy is in the superheated region. Then to find the temperature, we went to the table A6. In table A6, we found that there isn't a direct value for this enthalpy in the table to find the temperature for that enthalpy. So we didn't. We found the uh, two values which these enthalpies was between those two values. Then by interpolation, we found the temperature for the enthalpy which we have in this example. Simply, you can see how we can use interpolation to find uh, also the properties which may not be mentioned directly in these thermodynamics properties table. The next state which we have is compressed liquid. If you remember, compressed liquid was the left side of the saturated liquid line, or this area which we call that compressed liquid or subcooled uh, region actually. Then how we can determine if the substance is in this state or this region, and how we can find the different properties for the material substance which is in this region. Like previous uh, states, or like superheated or saturated uh, region, we have also another table A7. As you can see here in this table, we have compressed liquid properties. Our this table A7 is for water, so we have compressed liquid for water. We have the different properties, specific volume. Uh, we have a specific volume. We have internal energy, enthalpy for different temperatures, and also different pressure. The structure of the table more or less is uh, similar to the what we had for the superheated region. So you can see for different region and different pressure, we have these properties. This is one method which we can come to this table and find the properties for the water. For example, in this table, for the water in which is in the compressed liquid region. But how we can understand from the information which we get usually from the question, or how we can understand in if the water or the substance which we have is in this compressed liquid region. First of all, you should know that the compressed liquid properties it depends on the temperature, and its dependency to the temperature is much higher than its dependency to the pressure. So what the temperature is more effective on the properties of the substance in this region or on the water in the region or compressed liquid region. To check if the substance which we have is in this region, subcooled region, we can use these different conditions similar to what we had for the superheated. High pressure, if the substance which we have has a high pressure, it may be in subcooled region. But we need to check again. We need to check if the pressure which we have with the saturation pressure. The saturation pressure can be found in uh, table A4. If you remember, you need to go to table A4, compare the pressure which you have for that substance or water we have here. You need to compare the pressure for you which you have for the water with the saturation pressure of water at the temperature which you have. If the pressure is higher than saturation pressure for that temperature, it means it is in compressed liquid region. And also you can check by temperature. If the in lower temperature also we have a compressed liquid, let's say for the substance. You can check again. You need to go to table A4. This is table A4. This is table A5. You can go to table A5 for the given pressure. Find the saturation temperature, then compare your temperature which you have for the substance. If it is less than saturation temperature, it means it is in this region. And also with specific volume, internal energy and enthalpy, also you can check if your substance is in this region, sub compressed liquid region or not. Again, you need to go to the table and check for given pressure or temperature, the specific volume which you have is less than specific volume for saturated liquid in that pressure or temperature or not. If it is less than that, it means it is in this region, in the compressed liquid region. Then, and also for UF and HF, we same procedure you need to do. And if it is in this region, you need to go to the table A7 and find the different properties like PF, UF, like V, U, and H for that method. So this is one method to find these properties, the thermodynamic properties for the substance in this region, in the compressed liquid. But we can also have an approximation, and we can actually guess the amount of these properties which we have here by some assumption. Usually we can assume that a compressed liquid may be approximated as a saturated liquid at the given temperature. So we can have also this approximation like what we have in this figure. Uh, this. If you notice here, for example, here is the TU diagram in the temperature which we have is 80 degrees Celsius. The energy or internal energy for saturated liquid at this temperature is this much. And now if we have the pressure is different from the saturation pressure, its U will be different, like this will be this one. But still we can approximate that the energy or internal energy for the substance at this state is equal to the internal energy for that liquid in that temperature in saturated liquid state or on this line. So we can simply approximate that these properties V, U, or H, specific value of energy, internal energy, or enthalpy, are equal to those properties for saturated liquid at the given temperature. For sure, it has uh, some amount of error because this is just approximation. The exact values are presented in this table, and this is just approximation. And later we will see an example how much is the difference uh, uh, and how much is error between these two methods when we find this property. And also we have another relation which is more accurate to find H. H is equal to H in this compressed liquid region is equal to the enthalpy for saturated liquid for that temperature plus specific volume for uh, saturated liquid in that temperature times pressure which we have minus uh, saturation pressure at the given temperature. So here what we need to use this equation is the temperature as you can see here. Then need to go to the table A4, the table A5 or A4 and find this information, and the P is given also. Then we can approximate H by this equation when it is in the compressed liquid region. We will see also an example how to use the equation. But the most accurate uh, method is using this table. First, you need to understand if it is in this region, liquid, compressed liquid or not by these conditions. If it is in this region, you need to go to this table and find the properties for water in this region. Also, the second method uh, is this one, and also we have this method. This method is approximation. We can assume that instead of compressed liquid, we have saturated liquid in that temperature. And simply, we have VF for that, or UF or HF for that state. In this example, we are going to compare. Actually, we are going to compare those two different methods, the approximation method and also the accurate method by using the table. Here we are going to determine the internal energy of compressed liquid water. So it is mentioned, it's already mentioned that it's compressed liquid. No need to check by table A4 or A5 at 80 degrees Celsius and 5 megapascal. So we have temperature and also pressure for the water here. Data from we can in part A of the question, we should use data from the compressed liquid table or A7, table A7. And part B, we should use saturated liquid data. Then we need, table A4 or A5, which we have. Then we need to compare the error between these two methods. So the exact method from table A7 and approximate method from table A4 or A5. At 80 degrees Celsius, the saturation pressure is 47.4 something. We know this because of from table A 4. For we can find saturation pressure for this temperature in table A4, and since 5 megapascal is higher than this saturation pressure, we obviously have compressed liquid. However, it was mentioned that part A from the compressed liquid table, table A7, we can easily find these properties. Let's go to the table A7. 5 megapascal pressure, temperature 80 degrees Celsius. 5 megapascal and 80 degrees. You can see here we have the internal energy here, and also we have internal energy here, 80 degrees Celsius, and here is 5 megapascal. We have all of this information in this table A7, so we just record them. Then we can find U from that table. B from the saturation table or table A4. If we go table A4, the saturation, the according to what I told you in previous slide, we need to find the energy for saturated liquid in that temperature. Temperature here is 80 degrees Celsius. So if we go to table A4, for this temperature, UF is 334.97. Let me see if I can find table 4. Yes, here, table 4. So here you can see temperature 80 degree Celsius. Let me just find UF for saturated liquid. You can see here. Simply, we can come to this table and find the energy for saturated liquid in the heat temperature which is given in the question. Okay, so let's go back to our example. So we found the UF for this temperature, which is this much. Then how we can calculate the error? Simply by this equation, the accurate method, which the approximation method minus uh, exact method or accurate method divided by the accurate method multiplied by 100. And you can see here the error which we have here is 0.34%, which is less than 1% error, which is seems to be acceptable method to find the properties of the uh, substance or water here in the this area in the compressed liquid. So also we can use this method instead of referring to the table A7. We can use this method to find the properties for the fluid, for the liquid which we have here in this region, in the compressed liquid region. The last important thing about these thermodynamics properties table is the reference state and reference values which we have in this table. If you notice in the table which we had have had up to now, you can see also here, for example, this is saturated water temperature table, table A4. You can see here we had this reference point, which is 0.01. Usually it is very hard to measure the U or H, I mean the energy of the system. We don't have any uh, method to measure internal energy or even enthalpy of a substance directly. So instead we can measure the changes in these properties. So to understand and find the changes and the amount of changes in these properties in different substances, we need to have a reference value. This reference state, which we select, it is imaginary reference and we select that state as a reference state, uh, imaginary, and we assign a value of 0 for a convenient property or properties at that state, like what we have here. For example, here you can see the UF is assumed to be 0, and also SF. You can see this is our reference value for the saturated water. Then the other, for the other states, for example, when temperature is increased, what we have for this U or for the S or even H is changes, changing in amount of change in the that properties by changing of the state. For example, here the temperature is increased, and also these, we imagine in almost zero temperature, 0 degrees Celsius temperature, internal energy is 0. It is just, this is a reference state, we assume it is 0. Then when temperature is increased to 5, its energy is also increased to this much. This is changes actually of the energy of the cycle. We have different methods to measure these changes, but we cannot directly measure the amount of that. This energy, as also we had a discussion about that in previous chapters. We can measure this change in the internal energy by knowing how much is the heat transfer of the system, how much is the work by system or on system. So we can measure the changes, but we cannot measure how much is the energy of the system directly. We can only measure it when it is changing, or we can measure the changes in the these parameters, this property. And reference state for water, you can see here is 0.01 degrees Celsius, and for this refrigerant is negative 40 degrees Celsius. In these two different tables also you can see this. And because of this reference point, we have selected for the as the reference state in these tables. Some properties may have negative values as a result of these reference states. Sometimes different tables listed different values for some properties at the same state as a result of using a different reference state. So according to this sentence, you may see different properties table for material because they may select different reference point for their thermodynamics table. But usually this is a standard, and usually these reference state are chosen for these thermodynamics tables. However, it doesn't make any consequences or any changes in our calculation, because in thermodynamics we usually are interested about the uh, changes in the properties, not the amount of properties actually. So we just thermodynamic, as we discussed earlier, uh, will be a study for a system when we have a change in the for energy of that system, when there is a work or there is a flow of energy in that system. So in thermodynamic, we are always dealing with the changes in the system, changes in the amount of energy of the system, change due to the work or due to the heat, if you remember in previous chapter. So because of that, usually the amount of the energy or U is not important. The changes in that is usually important in thermodynamic uh, pro problems or questions. Next, we will have an example, which is uh, actually a comprehensive example to how we can, you know, find different properties in a table by some of information about some properties, then how we can use those information to find the other properties in that table. Here is an interesting example of how we can use the information which I told you about the tables to complete this table, which is which some parts of that is missed, and we are going to fill this table by the techniques and method which I told you in this session about the thermodynamics table. So let's see how we can fill these, the missed uh, places in this table. As you can see in this table, we have uh, different states, A, B, C, D, E, 5 different states. And the information which is given in this table are the temperature, pressure, uh, internal energy or energy, and quality, and also phase description for that state. And as you can see here, for different state, we have some of this information, and we are going to see how we can find these properties, as you can see here, according to the others. So here in part A, we don't know how much is temperature, but we have the pressure. We don't know how much is U, but we have X as the quality for this. So, and also for state B, you can see we have temperature, but we don't have pressure. We don't have quality, and we don't know how is the phase of the water at this state, and so on. You can see we need to find the state for different states, and write the phase for that state, which it is in saturated, which is saturated liquid, saturated vapor, or saturated liquid vapor mixture, superheated or superheated vapor, or compressed liquid, according to the information which we can find for these properties. So let's see step by step for different states. For a state 1, the quality is given. When we have a value for quality, like what we have here, 0.6, it means 60%. We have a mixture, saturated liquid vapor mixture, and 60% of that mixture is vapor. This is what we can understand from X for this state. And 40% of that is in liquid phase. Therefore, we have saturated liquid vapor mixture. So we should write here saturated liquid vapor mixture for this. And also we know its pressure. So we have saturated liquid vapor mixture with this much of pressure. How we can find temperature and U? By these two information, we know that the temperature also should be saturation temperature. We can go to the table A5, and we should find the saturation temperature with this pressure. Pressure is 200 kilopascal. Here is 200 kilopascal. So saturation temperature is 120.21 degrees, what we have here as well. So we found the saturation temperature. We should write here 120.1 degrees Celsius. What about U? At this pressure also, we need to find U. But here, as you may know from previous slides, for the saturated liquid vapor mixture, For U, we need to find U average. And if you remember, we had this equation to find U for a mixture or saturated liquid vapor mixture. So we should use this equation. U is equal to UF plus XUFG. UF also we can read from table A5 and also UFG. Let's go back to table A5. For this pressure which we have, we need to read UF and UFG. So let's go back to our equation. So we have UF from the table, we have UFG and also X, which is given here in the table. And finally, U will be 1790.26. So we found all of the information which was required for a state 1 or a state 8. Part B. In part B, you can see we have temperature. We have the temperature and also we have the temperature and also we have U. So what we can do here, but we don't know, we don't have any amount, any value for X or quality, so we cannot guess the phase just by these two information. What we can do is to, we need to go to table A4 according to the temperature which we have. We need to go to the table A4 for this temperature, which is table A4 for the saturated water. Then find the UF and UG for this temperature. Then we need to compare the U or energy which we have here in this table with UF and UG which we can find from the table A4. If U which we have here is less than UF for this temperature, it means we have compressed liquid. If our U in this table is between the UF and UG for the 125 degrees Celsius temperature, it means it is in saturated mixture. And if U is higher than UG, it means we have a superheated vapor. Okay, our U here is 1600. Let's go to the table A4 and see the temperature for the, let's see the energy for this temperature. Okay, the temperature is here. We have temperature, saturated water temperature table. The temperature, we found the temperature 125 degrees Celsius. Let's see how much is UF, and also here is UFG and UG. Actually what we need is UF and UG. Okay, we just record them, then compare our UF with those values. Here you can see also UF 500 something, UG 2500 something. What we have is 1600. So it is in accordance with the second condition. It means this state is also in the saturated mixture. So the value which we have fall between UF and UG, and it means we have saturated liquid vapor mixture. Then the pressure also for this state should be saturation pressure for this temperature. Again, we need to go to the table A4 and record and find the saturation pressure for that temperature. So you can see also we have here the saturation pressure for this temperature which comes from the table A4. And also we can calculate quality X by information which we can get from this table. Again, we need to go to table A4, find UF and UFG. Okay, table A4 again for this UF uh, and UG and also UFG, all of them in the table. We have U here, UF and UFG from the table. Then we can find X from the table. It means uh, about 53.5% of the mixture here is vapor and the rest is in liquid phase. We could also do same for the and also by this information we can find age and also other properties for these states. So here is saturated mixture and also we found the X and also pressure. All of this information also is now clear for part C. Part B. Part C, what we have in part C, let me just separate part C, what we have and what we need to find for these states. In this state, we have pressure and energy. You can see it is more or less, it is similar to part B. The only difference here is in part B we had the temperature, here we have pressure. So this time instead of table A4, we need to refer to table A5 to find the U and UF and U. Then we need to compare this U, which we have here, with UF and UFG for this pressure. Okay, so we have the pressure 1000 kilopascal. So let me just find that 1000 kilopascal. We need to come to this table, and for this pressure, we need to find the first of all the temperature. First, we need to understand if it is in which region it is. So we have the pressure. Let's see, just find U. This is UF. This is UG. We need to record them, then compare with the U which we have here. UF and UG for this pressure are 761 and 2580. What we have here to now 2950. So what we have here is superheated vapor. And the temperature at this state is determined from the superheated vapor table. So uh, to find temperature for this state, and also X here, it doesn't make any sense because we have superheated, so it is 0 or how we can also write 1, but it is meaningless, so we don't have quality for this uh, state as well. And we need to find temperature for this pressure. Again, we need to go to table A6. We have pressure. We have pressure also in this table. Then we need to find temperature for this pressure, which I'm not going to do that because this value is not directly in the table, and we need to do interpolation to find this temperature. The procedure is same as the interpolation process is same as the previous example which we had, and simply we can find the temperature for this pressure by interpolation, which will be 395.2 degree Celsius. And what about part D? In part D, what we have here actually is the temperature and pressure for this. And we don't know how much is U, how much is X, and we don't have any description about the phase. What we need to do here, we should select which one of temperature or pressure can be the basic for us. But usually it's better to select T and refer to the table which is according to the temperature. So we go to the table A4, and for this temperature we need to read saturation temperature. If saturation or vice versa, you can go to the table A5 and see the saturation temperature for this pressure. We have pressure 500, then we should find T saturation for this pressure. Then we should compare that saturation temperature for this pressure with the temperature which we have. If T, which we have here, is less than T saturation at the given pressure, we have compressed liquid. If it is equal, they are equal, we have saturated mixture. And if our T here is higher than saturation temperature at this pressure, it means we have superheated vapor. Okay, here pressure is 500 and uh, temperature is 75 degrees Celsius. Let's go to table A5. Okay, 500 kilopascal we have here. 500 kilopascal. Temperature, saturation temperature is 151.83, which is obviously the given T value is 25 degrees Celsius. What we found uh, in the table is 151.83 degrees Celsius, which is obviously higher than our temperature. And it means what we have here is compressed liquid. So we can simply refer to the table which we had for the compressed liquid and read this information U, uh, the energy for this temperature and pressure in the table. But in this case, we can also use this equation or the approximate uh, method. If you remember, we can use saturation liquid instead of the compressed liquid. The properties of saturation liquid are identical to the properties of the uh, compressed liquid which we have here. So instead of table which we had for compressed liquid, we can refer to table A4 again for this temperature. And please notice, if you do this approximation, you need to refer to the table which is prepared according to temperature. Like for saturated table and uh, which is according to the temperature, like what we have here, that the properties of water when its phase is saturated water, and the table which is prepared according to the temperature. So you need to come to this table and read the properties of saturated liquid like UF, then record that as the properties of the compressed liquid which we have here, which is 313.99 kilojoule per kilogram. Part E, and also we have also U here, and X is meaningless in here. And the part E, the quality which we have is pressure, and you can see here that X is 0. It means we have saturated liquid at that specified pressure. Then the temperature X0 means there isn't any vapor in the mixture. So it is saturated liquid. Then we need to go to the table for saturated water, and for this pressure which we have here 850, find the saturation temperature. if you go to table A5 and find for this pressure, if you go to table A5 for this pressure, find the saturation temperature, it will be this much for this pressure, and also the U will should be for the saturated liquid, or UF, for this pressure, which is 131 kilojoule per kilogram. So simply you can see how much these tables are useful methods, and how you can use them to find different properties or in different states, and also you can find the phase of the material according to the property as well.